Good. So it's a pleasure for me to introduce you Paul Carley, that for many of you know him already very well. So he has been here already before, and you know him from conferences. He's a great expert on MHD wave theory in magnetic fields. He has a long trajectory of work in this research. He's a great mathematician, so he's done his PhD thesis, I think, in 1980, in Monash. And then he has been traveling in UK and United States, visiting postdoctoral positions. After finally, he's now a full professor in Monash University in Australia. So he has been one of the first proposers of mode conversion theory and its importance for solar seismology. Alfvén wave, mode conversion, waves and flux tubes, different types of instabilities. So these days he's visiting us as a several Ochoa visitor for 2 months, sabbatical visit. And he's sitting in the office, which is a visitor's office in the 3rd corridor, so you can come and talk to him. So it's a pleasure for me to have his talk today on seismology of magnetic sun, the wounded sun. And please, you have
Thank you, Elena. It's very nice to be here, apart from yesterday's weather, of course. So I'm going to give a little bit of an overview of the sun's oscillations and how they interact with its magnetic field. And in particular, I'm looking at the scale of active regions, sunspots and so on. So I'll say a little bit about the global scale. I'll say nothing about the very small scale, where all sorts of interesting things happen too. I'll mainly concentrate on the scale of active regions. And my thesis really here is that on that sort of scale, active regions are like open wounds in the surface of the sun. They let things in and out, and they affect what's going on both in the interior and in the atmosphere. So that's one of the stories that I want you to take away today. The old story where we thought of the sun as being a bunch of separate layers: interior, photosphere, chromosphere, corona, I think has had its day. We can't do that anymore. So I'm going to give you a bit of a view about the physics of why we can't do that, why everything is connected. All right, so I'm going to be talking about some work that I've developed over the last few years with a number of collaborators, including my student Shelley Hansen, who finished recently, Hamed Maradi, who until recently was my postdoc, Elena Kamenka, who you know very well, and a bunch of other people. So firstly, let me just say a little bit about the sun's global oscillations. I know this is a general audience, they're not all solar physicists, so just a little bit about what are sometimes called the 5-minute oscillations of the sun, but were known about since the 1960s, not understood for a little while, but then quickly we realized that they are in fact just the normal modes of oscillation of the sun. So we can take the sun and expand its oscillations in spherical harmonics in the usual way that everybody's familiar with. There's a particular mode. Don't ask me to tell you which one it is. I haven't counted the nodes. But you have 3 quantum numbers: n, which is the radial quantum number. It's basically a measure of how many nodes there are radially going into the sun. L, which is the spherical harmonic one. It's telling you about the horizontal component of the wave vector, so to speak. And m, which is the azimuthal one, the theta component. And we can do a k-omega diagram, so a familiar sort of thing, angular degree L, or in other words, horizontal wave number, and frequency. And we see a whole bunch of distinct frequency bands. So the lowest one there is the F modes. The F modes are just surface gravity waves. That's what you get when you throw a stone in a pond of water and waves, the ripples go across. That's an F mode. The next one above that is the P1, then there's P2, P3, P4. The P modes are pressure modes. They're essentially sound waves propagating inside the sun. I'll say more about that shortly. So that's one view of it, and that corresponds to the view here on the right hand side. So those are some P-mode eigenfunctions. So in other words, all we're doing there is looking at those spherical harmonics and digging down in radius and seeing what is it? This is a pressure, I guess. The pressure or the displacement or the density or whatever you like is varying with, is there a pointer? Okay, so here's the surface and we have oscillations going down and similarly here. So this one is trapped here, this one is trapped up higher, so different N's and L's and M's, well M doesn't make much difference, but different L's and N's are trapped at different depths. So some of them are trapped in the convection zone, some of them get down below the base of the convection zone, some of them might reach right into the core. And of course, we can sit around on our spacecraft or with our telescopes, and when these waves come up to the surface, we can ask them where they've been and what they've seen. And that's helioseismology. However, another view is this view. So this is the ray perspective. So, as everyone's aware, oscillations can be described in a number of different ways. It's not saying that they are one or the other. It's just a useful technique to think about. So we can think about rays. So here we have short skipping rays. So it goes skip, 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 and deep skipping rays. So the deep skipping rays are associated with these modes that go down deep, and the shallow ones are associated with modes that don't go very deep. But don't think that each one of those corresponds to one of these. In fact, to make one of these, you need a whole bunch of those to put them together, and you can't actually do it perfectly. So it's really sort of expanding in a different basis mathematically. You are describing your oscillations either with the normal modes or with rays. Just a different way of thinking about it, and they're both useful. Now, it's often said that well, the sun, a lot of stellar astronomers thinks the sun is boring, right? I mean, you all know this. There are a couple of reasons why the sun is not boring. One is it's got some reasonable magnetic activity, not as magnetically active as many younger stars, but still it's got some magnetic activity, which is interesting, exciting, tells us a lot. But also it's damn close. So, in fact, the problem with the sun is we have too much data. It makes a total mess of our theories. I mean, theory would be so much easier if we were looking at the sun from a parsec away. But we're not. Unfortunately, we're too close, so we see all sorts of things that we shouldn't see. However, sometimes it's worthwhile, sometimes it's useful to look at the sun as if it were a star a long way away. So there's several instruments that do this. One of them is Bison, which has been running for a long time, over 30 years or something, I think. It's a long time. And it essentially is just looking at a full disk. And you can have a look at the oscillations of the sun here. So this is frequency, so that's about 3 millihertz. So most of the sun's power is peaked around 3 millihertz. And 3 millihertz corresponds to 5 minutes roughly. Hence the 5-minute oscillations. Alpha Cen B is just slightly higher in frequency. Alpha Cen A is a little lower, and so on. So here's a bunch of different solar-like stars, each with different frequencies, much like a violin, a viola, a cello and a double bass are basically the same thing but different scales. So they have different natural frequencies of oscillation. Actually, it has been said, and I don't know who first said it, but I think it's interesting to just explain to people what helioseismology is. Let's say you had never seen a cello in your life, you knew nothing about it. You were blindfolded, taken into a room, and somebody played the cello. You were then taken out and asked to draw it from the sound. That is helioseismology. Good luck. So this is on the large scale. We could go in and look at, on a much smaller scale, look at, and see all sorts of little splittings, relationships here between different peaks, and they tell us, they tell the astroseismologists in particular a lot about the star they're looking at. I'm not going to go into that, but there's a lot of information in these low degree power spectra. Now, I'm talking about the magnetic field of the sun and how it interacts with the oscillation. So the first question is, well, does the magnetic field have any effect on these global oscillations? Yes, but at quite a low level. What we have here are from Bison, over 3 solar cycles, the frequency change essentially as the solar cycle varies, and you can see there is a distinct change. It's fairly clear, but here we're at the level of less than a microhertz. Normally we're dealing with waves of 3-4 millihertz, and now we're less than a microhertz. So it's well less than 1 part in 1,000. And these different pictures are basically showing how that correlates with different measures of the solar activity, and they do better or worse. I'm not going to go into that. So there is an effect, but let me just say in a very loose sense, and if some people were in the room they would shoot me for saying this, but they're not, so I will. Simple interpretation of this is that the magnetic effects are very shallow surface effects. And what's more, they're sort of dappled across the sun, so the filling factor isn't one. So the waves that we're mostly looking at, especially at the frequencies 2, 3, 4 millihertz, don't really feel those magnetic fields very strongly. Hence the effect is small. All right, so there was our spherical sun. Now, is the sun spherical? Can we have a vote on yes or no? This is actually from just a couple of weeks ago. And the sun doesn't look very spherical from this point of view. So this is extreme ultraviolet, taken by the AIA instrument on the Solar Dynamics Observatory. And here's a close-up of a sunspot from the Swedish Solar Telescope, not a million miles from here. So we have structure. We have smaller structure than the global. So that's what I want to home in on here. Now, what about the atmosphere? So here are some what are called Alfvénic waves in transition region and corona. Waves sort of oscillating around on magnetic field lines, flux tubes, etc. It's a complicated picture. It's going all the time. It's ubiquitous. And the ones that we can see are transverse. Now, according to McIntosh et al. In 2011, there's actually sufficient energy here to power the quiet solar corona and the fast solar wind. So potentially these waves that are magnetic in nature in the corona can be important for the global structure of the outer atmosphere. Here's a figure from a famous paper by Steve Tomczyk et al. In 2007, which was, I think, the first identification of Alfvén waves. They called them Alfvén waves. There's been a lot of discussion about that since. But transverse waves in the corona. And here's a power spectrum for them that was observed. And we notice a peak here, a bump, at where the sun's P-mode frequency is, the 5-minute oscillations that I was speaking of before. So there's obviously quite a contribution here. Now, I would have to say that this probably greatly underestimates the power that's actually there. It's very difficult to look at oscillations in the corona because the corona, of course, is optically thin. You're seeing a whole bunch of oscillations over a big line of sight. Some are coming towards you, some are going away from you. It's all cancelling out. So the power is probably much greater than this, and that's actually what that McIntosh et al. Paper 4 years later said, which was the follow-up. So the point here is that there is at least some coupling between these oscillations in the corona and the internal oscillations of the sun at these sorts of frequencies. So some observational evidence for that. All right, so now I'm going to get to the real subject of this talk, which is the MHD waves in strong magnetic fields and the coupling over many scale heights. All right, so let's just decide what's important here. So here's the spherical harmonic degree. So in helioseismology, well, those sun as a star things, the bison ones that we looked at before, they were looking at L equals 0, L equals 1, 2, and maybe 3. With local helioseismology, looking at areas on the sun rather than the whole sun, we're normally looking at L equals 50, 100, 400, up to 1,000 or more. So there's a range of different L's that we might be looking at. Here's the horizontal wave number, and that's the typical wavelength. So we're looking here at wavelengths of order 5, 10, 20 megameters or so. On the other hand, in the photosphere and chromosphere, the density scale height is maybe 150 kilometers. Much, much smaller than the sort of wavelengths you're dealing with, and much smaller than the size of the sunspot, which is maybe 30 megameters across. So any wave that's coming into this region is going to see first and foremost that vertical stratification, the gravitational stratification. That's the most important thing. So we can essentially ignore for the moment the variation horizontally of the background and just look at the vertical. Now that variation in the density rho feeds through into the Alfvén speed, which is the magnetic field on square root of rho. So the Alfvén speed increases greatly with height. Typically in a sunspot umbra, the sound speed and the Alfvén speed might be comparable. But as you go a few hundred kilometres above, the Alfvén speed is much larger than the sound speed. This is related to the concept of the plasma beta, which is a terrible concept. I think it should be banned by the United Nations. Because everybody is always talking about the beta equals 1 layer. Everything happens at the beta equals 1 layer. Can anybody show me anywhere in the equations of magnetohydrodynamics where beta occurs? Beta is nothing. Beta is it's the ratio of the gas and the magnetic pressure, and it has no effect on the physics. The thing is that what is important on the wave physics is the relationship between the Alfvén speed and the sound speed. Now, as it happens, the ratio of the two, well, the ratio of the two squared is essentially beta, close to. There's a gamma on 2 in there. So by pure dumb luck, beta equals 1 is around where interesting things happen, but it's got nothing to do with the fact that the pressure, the magnetic and the gas pressure are equal there. Okay. All right. So what I really want to get to here is that there are 4 processes that are crucial in this story. So I'm going to go through these 4 processes. And I'm told reliably that the astronomers can remember 4 things. So hopefully when you leave this room, you will remember these 4 things. These are the 4 things I want to really emphasize. The ramp effect, I'll explain what these are shortly. Fast to slow mode conversion, fast wave reflection, and fast to Alfvén mode conversion. Those 4 processes, which are all separate in a way, all take place in these strong magnetic field regions. I'm going to neglect the horizontal structure, as I said before. That brings in a whole raft of other considerations. All right, the ramp effect. The ramp effect, as far as I know, wasn't called this, but it was discovered by Bell and Roy in 1977 in a paper which I knew at that time, actually. I read at that time, and along with everybody else, forgot. So for about more than 25 years, everybody forgot about this paper completely. One is it was a bit of a messy paper. It's got lots of typos. It's got some mathematical errors. It's a bit of a pain in the neck of a paper, but basically it was correct. And the idea is that the acoustic cutoff frequency. Now the acoustic cutoff frequency is a strange concept too. I won't go into that. But it basically tells you where these skipping rays reflect. See, why are these waves doing this inside the sun? They're reflecting down below at what's called the Lamb depth, and that is basically where omega equals the sound speed by the wave number, the horizontal wave number. So that's just any sound wave will refract there, or reflect. At the top, it's essentially the acoustic cutoff frequency. So when it comes up and reaches this acoustic cutoff frequency, which in the low atmosphere of the sun is about 5 millihertz, it reflects. It can't propagate above that. So that's your top boundary condition. The point about the ramp effect is that when you've got a strong magnetic field, it modifies that acoustic cutoff frequency. it multiplies the frequency by cos theta, where theta is the inclination of the magnetic field. So for vertical magnetic field, it doesn't touch it. Theta equals 0. So the acoustic cutoff frequency just stays at that 5 millihertz. As the field goes over and theta increases, the effective acoustic cutoff frequency drops. That's the ramp effect. Essentially, there is a ramp here that waves can climb up. They couldn't get up when the field was like this, but when you give them a ramp, they can climb up and they can get into the atmosphere, they can propagate. So this was all rediscovered observationally in a way by Stuart Jeffreys et al. In 2006, who did some observational work and basically found that the theory of Bell-Lenoir was completely correct in the sense that, and this result was correct, that as Jeffreys et al. Stated it, there are magnetoacoustic portals, doors, or windows I prefer to think of them as, in the sun. And this is sunspots, but it's also smaller scale network between supergranules, etc. So that's the first way that we open up the atmosphere of the sun to what's happening in the interior. Inclined magnetic field. All right. So let's say now that because of the inclined magnetic field, these waves are able to get up. They can go up higher than they would have done. Normally they would have reflected maybe just a little below the photosphere, depending upon their frequency. Now what happens when they meet the layer where the Alfvén and the sound speed are equal? It's what I call the equipetition layer. So remember, as I said before, beta means nothing. What is important is where the Alfvén speed A is equal to the sound speed C, because that's where your magnetoacoustic waves can talk to each other. You're on a train. You're going along a track. There's a parallel track and another train going on that in the same direction. Your girlfriend's in the other train. You want to give her an ice cream. You lean out the window and give her the ice cream. When can you do that? I'd suggest if you're going to try that, and I don't recommend it, if you're going to try that, do it when the two trains are going along at the same speed. If they're going like this, definitely don't try it. Okay? The point is that when they're going along at the same speed, they can communicate. And it's the same thing with the fast and the slow waves, magnetoacoustic waves. And when are they going at the same speed? Basically when it's A is equal to C. So that's when they can give each other ice creams or energy, as whichever you prefer. All right, so let's say here's the magnetic field, the blue field lines there, and let's say I've got a wave coming up here with a wave vector k. Now everything is going to depend upon this angle alpha that between the magnetic field and the wave vector k at this equipetition surface. That's what I call the attack angle. Basically, if the attack angle is small, then this wave that's coming up can just go straight through. I say that's high transmission. Transmission is close to 1. If, on the other hand, it's coming up at an angle like this and it's crossing at a large angle, there's hardly any transmission and it's mostly conversion. So let's get this right. What's transmission? So this wave here, remember it's a sound wave below the surface. It's coming up, transmitted, it's going to stay a sound wave. Now a sound wave down here is a fast wave. That's because the sound speed is greater than the Alfvén speed in the interior. Once we get above A equals C, it's the other way around. the sound wave, the acoustic wave, is now slow because C is less than A. So it's changed from being a fast wave to a slow wave, but it's stayed acoustic. It's gone from acoustic to acoustic, and that's what I call transmission. And we have an approximate formula here that I calculated analytically. The transmission is approximately given by e to the minus pi k hs sine squared alpha. Hs is sort of a scale height in here. I won't go into the details of it. K is the just the wave number, and alpha there is our attack angle. So if alpha is 0, we get almost total transmission. It goes through as a sound wave. The conversion is 1 minus t. So what is very crucial is you've got these waves coming up from below the surface, meeting the A equals, they're allowed to get through by the ramp effect. They meet the A equals C surface, and there they can split into fast and slow. So here's a picture of how this happens. This is actually from a calculation. It's not just schematic. So let's say we've got our incident fast wave coming in here with energy 1. So red is energy 1. It comes up here, meets the A equals C surface, that's this, and it mode converts there partially into the slow wave, which is an acoustic wave, and that's just going to run along the field lines. It's a slow wave, slow MHD waves have to go along field lines. So it's just a longitudinal wave. It's like a sound wave in a tube. Just goes along the field lines. Can't bend the field, doesn't have enough strength. It goes up here, and that's carrying most of the energy in this case. Yellow, it's carrying maybe 75% of the energy because the attack angle here was small. It's basically coming up almost parallel to the magnetic field. On the other hand, there is some conversion to the fast wave, and the fast wave then comes up, turns over, reflects, and goes back down. And when it passes through A equals C again, it splits again. So that's the picture. The dots, by the way, are 1 minute apart in group travel time. So it took 1 minute to go from here to here to here. This thin black curve is what the ray would do if there was no magnetic field. So in the non-magnetic sun, it's going to come here. 1 minute, 1 minute, 1 minute, 1 minute, 1 minute, 1 minute, 1 minute. So it's taken an awful lot longer to get through. So this is going to affect your helioseismology a lot. The wave is going to get through this active region much faster than it would in quiet sun. All right, let me give you another view of this. So this picture on the right is what we've just seen. This picture on the left is exactly the same thing, but in phase space. So this is Z, that's the height here, and this is KZ, which is the vertical wave number. And the vertical line is the A equals C layer. So in other words, we should expect things to happen when we get to this layer. Well, I'm going to start a little movie. Now, in phase space, going once around that lobe there, this interior lobe, once around that lobe is equivalent to doing one skip in physical space. So the left-hand picture is ZKZ space. The right-hand picture is normal physical XZ space. So one skip means you go around once. So that's the bottom of your skip, and that's the top of your skip. And normally, if there's no magnetic field, you would just go around once, and that's one skip, and then you go around again and again. So let's actually see what happens. You can see the little particle here, goes here, splits again, goes back down. And this corresponds exactly to what's going on the right-hand side. So let's see if we can watch two things at once. It stopped for me. Okay. So there, splits there. You see it split. So this is the fast waves, and this is the slow waves. And they mode convert when they come close together in phase space. This is the two trains coming close together when you can hand the ice cream over. All right, so here's now the overview. So here's our process 4 now. Fast to Alfvén mode conversion. So trying to put everything together in a way. Here's our fast wave coming up from below. It's able to get up high because of the ramp effect. It then meets the A equals C layer and it mode converts. Some energy goes into a slow wave, some energy goes into a fast wave. The fast wave reflects. Why does the fast wave reflect? It reflects because its dispersion relation is basically omega is equal to AK, where A is the horizontal, A is the Alfvén speed and K is the wave number. So when, if you have a particular KZ, KX, then KZ becomes imaginary once you get above where the Alfvén speed is equal to the horizontal phase speed. So it's always going to reflect. Now the important thing is where it reflects, around about there's a further mode conversion. And that is the fast wave can partially convert into an Alfvén wave. An Alfvén wave is just a wave on a string. It's just a shaking of the magnetic field lines. So this fast wave reflects and goes back down and gets involved in the seismology again. But the Alfvén wave can go up into space perhaps. And that can contribute to these coronal oscillations that we saw before. Now, by the way, this is a 3D process. That's a projection. If everything is happening in a 2D plane, there is no conversion to the Alfvén wave. So you need the wave to be slightly out of the plane that the magnetic field is in. So if the magnetic field is in this plane, like this, if your wave is going this way, there's no conversion. It's got to be doing this. All right, now, what if the field is inclined the other way? So if it's inclined like this, so again, we come up, again you can convert to the Alfvén wave, but this is going to be an Alfvén wave going down. So this is all some theory that my student Shelley Hansen and I did about 3 years ago. And I'll give you some pretty animations, I think. All right, this is work with Jesse Andrews. Let's first take the case of horizontal magnetic field in a stratified atmosphere, so the density is dropping off exponentially with height. So I send in a fast wave ray, sort of a ray bundle, a fast wave. It's going to go up and reflect and go back down. Now it's slightly out of the plane that you see here. So here it is. It's going up, reflecting and going down. And remember that the field lines are all horizontal in this case. That green line is where the Alfvén resonance is. I won't go into the mathematical details of it. That's the Alfvén resonance for the central line, which is this red line in the ray bundle. So if we actually watch this as a movie, well, actually what you need is Polaroid sunglasses. Does anybody have any Polaroid sunglasses? You see, you can't see this unless you have the Polaroid sunglasses. Because the Alfvén wave is actually polarized out of the board here. It's going to be oscillations which are coming out of the board. Let me fix this for you. I should have told everybody to bring their sunglasses. So there, I've turned it on so you can see the Alfvén waves now. So the grayscale is essentially the pressure perturbation. That's what the fast wave has. And the out of the board velocity is shown by the red and the blue. And if we watch that for a little while, there is the purest case of mode conversion I think you could imagine. And that's sort of a semi-analytic calculation. We had to sum a whole bunch of terms in a Fourier expansion to get that, but that's what it is. So you've got your fast wave going up and reflecting, but creating Alfvén waves which then go out along the magnetic field line. And as they do so, they're phase mixing. Notice that the length scales involved in those Alfvén waves are getting smaller and smaller. And so you expect to get some thermalization at some stage out here. You're creating very small scales. So this direction. Yeah, you can think of it that way. I mean, we did this purely as a mathematical thing, but so the density is dropping off with height, with x. Let's do the same thing now. Instead of sending in a ray, which is a tube, I'm going to send in a burst. So a single burst everywhere. Here it comes. That's our fast wave, reflecting, going back down, and look what it's left. Alfvén waves going along the horizontal magnetic field line. And as time goes on, those Alfvén waves phase mix, smaller and smaller scales are produced and ultimately must thermalize. Now that's with just horizontal magnetic field. Let's do it with vertical magnetic field. So again, this is a semi-analytic solution. So on the left-hand side, what I'm going to do is send in our fast wave from below. So a whole bunch of fast wave coming here and going in this direction and reflecting. And we want to see whether that excites any Alfvén waves. And remember, Alfvén waves are shaking things. So there we are. These fast waves have come in here and they're shaking the field lines and creating these Alfvén waves. The Alfvén speed is so large that the wavelength is now very large, and it just really looks like a flapping process. But let me play that exact same game, do exactly the same thing, but have the fast wave go the other way. In other words, it's coming like this. Everything else is identical. Let's see what happens now. Can you see that? There's hardly any motion up here. So coming this way, we made a lot of upward going Alfvén waves. Going this way, we made practically none. And that fits perfectly with this theoretical picture. Basically what's happening is if you're going in a direction that's with the magnetic field inclination, you're going to make Alfvén waves that go upwards. If you're going against the inclination, you're going to make Alfvén waves that go downwards. Alright, so that was all very well in nice, simple, uniform inclined magnetic field, but what about the real sun? What about a real sunspot? So here's some calculations that Elena ran a few years ago. So this is a sunspot model So the A equals C layer here, I think, is I don't know if it's the dashed line or the full line. Okay, now this should be squashed a lot. The scales aren't right here, so those field lines are actually much more inclined than they look in this picture. And we've sent in waves here coming this way, and so over here the wave is going with the magnetic field inclination, so it makes Alfvén waves that go upwards. Fluxes are red, they're positive, and over here on this side of the spot the wave is meeting the magnetic field leaning the other way, and so the Alfvén waves that it's making are going downwards. They're blue. Fluxes are negative. So that all fitted extremely well with the general theory. I won't say too much about that. Yeah, look, the idea here is that reducing this problem to a sort of a problem in a box, a uniform inclined magnetic field, put a driver down a few megameters below the surface and look at what comes out the top and solve this as a boundary value problem mathematically. It has to be done numerically, but it's basically ordinary differential equations, not partial differential equations. And everything depends upon our angle theta and angle phi. So let me remind you about angle theta. It's the inclination of the magnetic field. And the angle phi is the angle out of the plane that my wave is compared to the magnetic field. Remember I said if phi is 0, if we're in the same plane, you get no fast to Alfvén conversion. You get fast to slow, but no fast to Alfvén. So these two angles, theta and phi, are actually crucial. And we can do a whole range of experiments here, have different thetas and different phis, and look at the travel time differences. This is doing helioseismology on it, time distance helioseismology. Or we can do how much energy is coming out the top. So this is the energy coming out the top in acoustic waves. This is the energy coming out the top in magnetic waves, essentially Alfvén waves. And it depends upon your theta and your phi. So we get most fast to slow mode conversion at around about magnetic field inclined around 30 degrees from the vertical, but with phi equals 0 in the plane. But conversion to Alfvén wave, we get most of that at, say, a slightly higher angle, 40 or 50 degrees in inclination, but coming across at, say, 60 degrees to that plane. Now, of course, on the real sun, you've got waves coming from all sorts of angles. So a sunspot, for example, is going to be a filter. It's going to filter waves. Certain waves it's going to do different things too, depending upon the direction that they're coming from. I won't go into the full details here, there's too much. Now that's from this boundary value problem calculation, but it was also tested in full-scale simulations using the Spark code. Hamid Muradi did this, and we found essentially exactly the same result, plus or minus the sort of the numerical errors that you expect to get. So travel time differences that depend upon theta and phi. I won't go into the details. But here we also did this with a sunspot model. So not just a uniform inclined field, but an actual axisymmetric sunspot model with a radial structure. All right, so I will finish up on that. Let me just say, just to prove to you that we really are coupling the seismology with the atmosphere, if we now put a transition region in, the chromosphere corona transition region, which is way up high, obviously atmosphere, does that actually make any difference to the seismology? Yes, it does. So this is with, that's without, this is the energy getting through the top without the transition region and with a transition region. Much the same sort of values, which is saying that we can actually get these Alfvén waves to get through the transition region. Up till this stage, people believed that maybe only a few % of Alfvén waves could get through the transition region. But those were Alfvén waves created down at the photosphere. We're looking at Alfvén waves actually created in the high chromosphere, so close to the transition region, and they are much more able to get through. Alright. Okay, so my summary. Active regions are wounds in the skin of the sun. Waves can escape and re-enter through these wounds. That has implications both for the solar atmosphere and the solar wind, as well as the solar interior. Why for the solar interior? Because the waves that have been out into the atmosphere and suffered these various effects, when they go back in, they will carry the memory of that. So the seismology of the sun is changed by the fact that there was this open window. If you don't believe me, go get a Stradivarius violin and bore a hole in the back of it about that big and see if the notes are the same. I suggest they won't be. So there are two types of mode conversion: fast to slow, which happens where the Alfvén and the sound speeds are equal, and fast to Alfvén, which happens near where the fast wave reflects. The re-entering fast waves carry a modified phase. Their phase has changed, and so they produce what's called a travel time shift to helioseismologists. In the early days of trying to probe sunspots with helioseismology, everybody was interpreting these travel time shifts as sound speed variations, which they are not, or at least not totally. There are these complicated magnetic effects as well. So you have to take those early results with a lot of, with a large amount of skepticism. The fast to slow causes negative travel time shifts, and the fast to Alfvén causes positive travel time shifts that partially undo each other. And we've also shown that this works in more realistic sunspot models. So this is work just published by Hamid Muradi and myself earlier this year. Okay, and because I'm always asked about sort of where Australia is and where Monash is and how this relates to Europe, because Europe is the centre of the universe, so if we took Australia and put it at the same latitude and superimposed it here, so you can see you're about sort of Brisbane. Now Monash University is in Melbourne, which is sort of here, which is like the south of Spain. And most of it's sort of Africa. So just to give you a view. Now that isn't a particularly reliable indication of weather. Obviously it's surrounded by ocean and that makes a difference and so on. But anyway, that'll give you a bit of a view. Okay, thank you very much.
We have some time for questions.
First of all, thank you for this enlightening talk. You mentioned that the oscillations, the magnetism modify the oscillations in some sense. But how can be the opposite, the other way around? Can the oscillations interact or organize the magnetic field in the surface? In my mind, I have the idea of the active longitudes. When you are in the cycle, you have some persistent activity emerging in some particular longitudes. Can that have to be with oscillations?
I don't think so. That has to be much deeper. That's got to be, I think active longitudes have to be stuck somewhere below the surface, because they last for a long time. And the sort of time scales that you have at the surface or in the atmosphere are couldn't sustain anything for that long. It has to be something in the interior. And in the interior, of course, the magnetic field is so weak compared to the gas pressure, etc., that really the magnetic field is just pushed around with wherever the flows are taking it, and buoyancy and so on. So I think that it can't be doing that, but I think in the atmosphere, waves can have an effect on the magnetic field. Waves can have an effect, for example, on reconnection. They can play an important role there, which can change the whole topology of a region. So I think where waves become important is at the surface and above. This is what I was saying before, that magnetic activity as far as oscillations are concerned is skin deep. Sunspots are like a pancake. They are very, very shallow. The Alfvén equals sound speed layer in a sunspot umbra, which is the strongest magnetic field you can get on the sun, 3 kilogauss or so, might be 400 or 500 or 600 kilometres below the surface, but that's nothing. Don't forget, sunspot is 30 megametres wide, and we're talking about the magnetic effects being sort of restricted to a few hundred kilometres. So all of the stuff going on inside the sun as far as waves are concerned hardly knows about the magnetic field, and that's what makes magnetohelioseismology so difficult. In the early days, and I was guilty of this, we were thinking, oh, we'll be able to probe down deep in sunspots and see what they look like and so on. But the whole thing is that whatever's going on down there has no effect on the waves. It's just this thin layer at the surface that does it. But then it opens up. It's, like I said, it's like boring a hole in the surface, and it opens up the whole atmosphere. So it allows you to connect things from interior to high atmosphere.
Thanks for this very nice talk. I am not an expert on this, but I have a question that maybe is completely stupid. It's possible that in some different kind of star, I'm thinking about M-dwarf, that are characterized by stronger magnetic field, the magnetic field is able to damp completely or at least strongly reduce the oscillation?
Oh yeah. In fact, I didn't go into that, but this is how I actually got into this game. We know this happens in sunspots even. The field there is strong enough. There were observations in the late 1980s by Doug Brown and others where they had a look at the P-modes, they projected them onto the surface and thought of them as like ripples on the surface of a pond going into the spot and then coming out of the spot. And what came out of the spot was maybe 50% less than what went in. So essentially sunspots were eating F-modes and P-modes. And the reason, well, there were a number of suggested reasons for this that were around for a few years, but Henk Sprout came up with an idea that was developed then a little bit by Tom Bogdan and Henk, and then I came into the story with Tom Bogdan and did a lot of work through the 90s. And we found that it was this fast to slow mode conversion. Essentially what's happening here is you've got your waves coming in, hitting the sunspot, and a lot of mode conversion to slow waves. And at that stage we were only looking at slow waves which go down into the interior. So these are waves which just go down and are lost inside the sun. Some of them will also go up. We didn't look at that stage, but that's what I was talking about here. But that process will definitely be happening in more magnetic stars. Some of these more magnetic stars have giant star spots, much larger and more powerful than anything that we see on the sun. And they, both because of their strength, but also their size, the filling factor, of course, is much larger. So they will take the P modes that are sloshing around inside the star and strongly convert them into waves, into these magnetic slow waves which go down into the interior, never to be seen again. So it's essentially they have absorbed them, they have damped them. So that's, I'm absolutely certain that's a very strong process. And there is a whole community, of course, in stellar physics that looks at that, runs sort of parallel to what we've done in the solar regime, but with a slightly different context. But yeah, that's a terribly important process.
Thank you. Okay, last question.
This is an even more stupid question. I was listening to your answer to the last one and looking at this great image up here, which is presumably what you see if you look through the center of the Earth, right? If it was transparent, that's what you'd see, I think. Is that right? Give or take the projection. Or is it not,
no,
is it not orientated?
Australia would be the right way up then. It's,
okay.
It's upside down here.
Sorry.
So there's a mirror involved.
Wait. I think that's still right, though. I think that's still right, anyway.
Cape York would still point north, wouldn't it?
Well,
yeah.
I said
okay.
That's what you see if you look straight through the middle.
Okay, go on. We can live with that.
I think that's true, isn't it? So the further south you are here, the further north you will see on the other side. It wasn't my question.
Yeah, go on.
So what you see if you look straight through, I think, unless it's not orientated left-right, I've no idea. I think it's what you see if you look straight through the middle.
I think the left-right orientation is arbitrary here.
Ah, okay.
The
cheating. Yeah, so whoever made the map, yeah.
The latitude is right.
But it's a great figure anyway. What I was thinking about is that you kept saying waves disappear in the center. Mm-hmm. Is that true? I rather like the idea that one side of the sun might respond in some very dispersed way to what's happening on the side, just as this figure here is showing.
I think that will happen in some circumstances, because especially associated with active regions, not just sunspots, but active regions more generally, you can have some field which sort of goes up and down like a serpent. So you can imagine sending some stuff down and it coming back up in another place. However, for much of the field that's going down deeper, the length scales of the slow wave become so tiny that they're actually, well, firstly they're going to get involved with the convection scales, and eventually they're even going to get down to sort of the molecular level where they're going to be damped out by molecular processes. You get to really tiny scales very quickly, simply because the Alfvén speed becomes so very small as you go down deeper. Simply the density is becoming large. So I think it would be difficult to really go sort of right through the sun and come out the other side with anything like that.
Okay, we are already a bit out of time, so let's thank Paul again.